Okay, today I'm gonna do a future engineering course. Let's begin. Welcome to future engineering. In this course, you'll learn about one of the most important steps on the way of to building a great machine learning model, future engineering. You'll learn how to determine which futures are the most important with mutual information, invent new futures in several real-world problems domains, encode high cardinality categoricals with target encoding, create a segmentation of features with k-means clustering, decompose a dataset's variation into features with principal component analysis. The whole hands-on exercise build up, just the introduction. The goal of future engineering is simply to make your data better, suited to the problem at hand. Consider apparent temperature, measures like the heat index and the wind chill. This quantities attempt to measure the perceived temperature to humans based on their temperature, humidity, and wind speed, things which you can measure directly. You could think of an apparent temperature as a result of a kind of future engineering, an attempt to make the observed data more relevant to what we actually care about, how it actually feels outside. You might perform future engineering to improve a model's predictive performance, reduce computational or data needs, improve interpretability of the results. A guiding principle of engineering. For a feature to be useful, it must have a relationship to the target that your model is able to learn. Linear models, for instance, are only able to learn linear relationships. So when you're using a linear model, your goal is to transform the features to make their relationship to the target linear. The key idea here is that a transformation you apply to a feature becomes, in essence, a part of the model itself. Say you are trying to predict the price of square plots of land from the length of one side. Fitting a linear model directly to the length gives poor results. The relationship is not linear. If we square the length feature to get area, however, we create a linear relationship. Adding area to the feature set means the linear model cannot fit a parabola. Squaring a feature, in other words, gave the linear model the ability to fit squared features. This should show you why there can be such a high return on time invested in future engineer. Whatever relationships your model can't learn, you can provide yourself to transformations. As you develop your future set, think about what information your model could use to achieve its best performance. Concrete formulations. To illustrate these ideas, we will see how adding a few synthetic features to a dataset can improve the predictive performance of a random forest model. The concrete dataset contains a variety of concrete formulations and the resulting product's compressive strength, which is a measure of how much load that kind of concrete can bear. Thus, the task of this dataset is to predict a concrete's compressive strength given its formulation. You can see the various ingredients going through each variety of concrete. We'll see in a moment how adding some additional synthetic features derived from this can help a model to learn important relationships among them. We first establish a baseline by training the model on the unaugmented dataset. This will help us determine whether our new features are actually useful. Establishing baselines like this is good practice at the start of the future engineering process. A baseline score can help you decide whether your new features are worth keeping or whether you should discard them and possibly try something else. So basically creating the random forest here. Then using cross validation, baseline. If you ever cook at home, you might know that the ratio of ingredients in a recipe is usually a better predictor of how the recipe turns out than their absolute amounts. Might reason that might reason then that the ratios of the features above would be a good predictor of compressive strength. Tableau adds three new ratio features to the dataset. So it's creating basically new columns that are ratio of the other columns. One column divided by the other. Which is a smart thing to do. And pretty much finding new new ways to see the relationship of the data. Wait, so there's no exercises? Okay. First, encountering a new dataset can sometimes feel overwhelming. You might be presented with hundreds of thousands of features without even a description to go by. Where do you even begin? Read 4 steps to construct a ranking with a feature utility metric, a function measuring associations between a feature and the target. Then you can choose a smaller set of the most useful features to develop initially and have some more confidence that your time will be well spent. The metric we'll use is called mutual information. Mutual information is a lot like correlation that it measures a relationship between two quantities. The advantage of mutual information is that it can detect any kind of relationship, while correlation only detects linear relationship. Mutual information is a great general purpose metric and especially useful at the start of future development when you might not know what model you'd like to use yet. It is easy to use and interpret it, computationally efficient, theoretically well founded, resistant to overfitting, and able to detect any kind of relationship. Mutual information and what it measures. Mutual information describes relationships in terms of uncertainty. The mutual information between two quantities is a measure of the extent to which knowledge of one quantity reduces uncertainty about the other. If you knew the value of a future, how much more confident would you be about a target? Here's an example from the Ames housing data. The figure shows the relationship between the exterior quality of a house and the price it's sold for. Each point represents a house. From the figure, you can see that knowing the value of exterior qual should make you more certain about the corresponding sale price. Each category of external qual tends to concentrate sale price to within a certain range. The much information the external qual has with sale price is the average reduction of uncertainty in sale price, taking over the four values of external qual. Since fair occurs less often than typical, for instance, fair gets less weight in the MI score. Technical notes. What we're calling uncertainty is measured using a quantity from information theory known as entropy. The entropy of a variable means roughly how many yes or no questions you would need to describe an occurrence of that variable, on average. The more questions you have to ask, the more uncertain you must be about the variable. Mutual information is how many questions you expect the future to answer about the target. Interpreting mutual information scores. The least possible mutual information between quantities is zero. When MI is zero, the quantities are independent. I have a problem with this notion because in my mind, nothing is independent from everything else because everything is connected. But I get the point. It's a lower relationship or lower direct relationship. Neither can you neither can tell you anything about the other. Conversely, in theory, there's no upper bound to what MI can be. In practice, though, values about 2.0 or so are uncommon. Mutual information is a logarithm. I have trouble saying this quantity, so it increases very slowly. Let me see how it's spelled.
logarithmic,
logarithm, logarithm,
logarithmic,
logarithm, logarithmic, logarithmic,
logarithmic,
logarithm. Next figure will give you an idea of how MI values correspond to the kind and degree of association a feature has with the target. So target, feature, MI score. Left, mutual information increases as the dependence between features and target becomes tighter. Right, mutual information can capture any kind of association, not just linear like correlation. Here's some things you remember when applying mutual information. MI can help you to understand the relative potential of a feature as a predictor of the target, considered by itself. It's possible for a feature to be very informative when interacting with other features, but not so informative all alone. MI can't detect interactions between features. It is a univariate metric. The actual usefulness of a feature depends on the model you use it with. A feature is only useful to the extent that its relationship with the target is one your model can learn. Just because a feature has a high MI score doesn't mean your model will be able to do anything with that information. You may need to transform the feature you first expose the association. The automobile datasets consist of 193 cars from the 85 model year. The goal for this dataset is to predict the car's price from 23 cars, such as make, body style, horsepower. In this example, we rank the features with mutual information and investigate the results by visualizing the data. The scikit-learn algorithm for MI treats discrete features differently from continuous features. Consequently, you need to tell it which are which. As a rule of thumb, anything that must have a float d-type is not discrete. Categorical, object, or categorical data type. Categoricals can be treated as discrete by giving them a label encoding. So I don't understand why anything that has a float is not discrete. Because even though it's a number, it can be a discontinuous function. Yeah. Yeah, but it makes sense because it's data, not function. I guess I get it. No. So X is the data frame copy, Y is the column that's the target value, then it's selecting for the columns. X the type. I don't understand this last line here. I guess it's filtered now. Scikit-learn has two mutual information metrics. In its feature selection module, one for real value targets, mutual info regression, and one for categorical targets, mutual info classify. Our target price is real valued. Next cell computes the MI scores for our features and wraps them up in a nice data frame. So creates the object first with X and Y and discrete features, which I guess is an additional parameter of this object. Then creates the series with this first variable, puts a name, index equals X columns, which is this. Sort values ascending false. Okay. Now a bar plot to make comparisons easier. Data visualization is a great follow-up to utility ranking. Let's take a closer look at a couple of these. As might expect, the high scoring curb weight feature exhibits a strong relationship with price, the target. The field type feature has a fairly low MI score, but as we can see from the figure, it clearly separates two price populations with different trends within the horsepower feature. This indicates that field type contributes interaction effect and might not be unimportant after all. Where the deciding feature is unimportant from its MI score, it's good to investigate any possible interaction effects. Main knowledge can offer a lot of guidance here. Data visualization is a great addition to your future engineering toolbox, along with utility metrics like mutual information. Visualizations like this can help you discover important relationships in your data. So here, it's probably doing the beginning steps. Setting matplotlib, load data, filtering the data types, should non-discrete. All discrete features should now have integer data types. For a column, I don't know what factorize does. Showing for regression, and these are the 33 steps from the tutorial. Whereas finding the correlation. I think you ran. So to start, let's review the meaning of mutual information by looking at a few features from the AMIS dataset. Just getting the future and plotting the graph. Understanding mutual information. Based on the plots, which future do you think would have the highest mutual information with sale price? High information. This looks too random, so it has to be one of these. But this seems like there's no change, so I think the first one. Yeah, year build should have the highest. The Ames data set has 70, 80 features, a lot to work with all at once. Fortunately, you can identify the features with the most potential. Use the make MI scores function using the tutorial to compute mutual information scores for the Ames feature. So is making x equals the data frame copy and y the target, which is the column of the data frame. Now examine the scores using the functions in this cell. Look especially at top and bottom ranks. And the scores is calling the function defined on the first cell with x and y. What am I scores? So overall quality is the biggest. Second for SV is the lowest. Excellent MI scores. Do the scores seem reasonable? Do the high scoring features represent things you think most people would value in a home? Do you notice anything in what they describe? So yeah, overall quality, neighborhood, guard. I think GR live area is garage life area, something like that. Garage area, no, so it's something else. I'm not sure what that means. But I think it makes sense. The issue though is that sometimes, a lot of times, the things can be counterintuitive. So if you don't understand a lot about the thing or you're trying to analyze, it can be a problem. Because I might think that this qualities make these features make people it makes sense, but in reality it's completely different. Some common themes among the most of these features are location, size, quality, year, types. These are all kinds of features you'll commonly see in real estate listings, like Zillow. It's good then that our mature information metrics scored them highly. On the other hand, the lowest ranked features seem to mostly represent things that are rare or exceptional in some way. This step will investigate possible interactions effects for the BLG type feature. This feature describes the broad structure of the dwelling in 5 categories: single family detached, two family duplex. The BLG feature didn't get a very high MI score. A plot confirms that the categories in BLG type don't do a good job of distinguishing values in sale price. The distributions look fairly similar, in other words. So here's a graph of the category of sale price. Still, the type of dwelling seems like it should be important information. Investigate whether BGD type produces a significant interaction with either of the following: above ground living area, so ground living area. Also, run the following cell twice, the first time with future and the next time with future most. So it's gonna plot sale price, BGD type. So one family seems to be linear relationship, increasing the price. The other ones are also linear but have steeper slopes, except for this one, maybe. The other ones are all lower. No, most, so. Or I have to change here again, I think. The trend lines being significant different. I'm not sure if I did this the right way, but yeah. It seems like when you increase most sold, increases the price. No, it's the same thing actually. It's just going to the right because obviously you're increasing the value. Trend lines being significantly different from one category to the next indicates an interaction effect. Discover interactions. From the plots, does BGD type seem to exhibit an interaction effect with either partially Vera or most? ground living area or also. I think yes, but I'm not sure. It comes from intuition, not from the data, from just seeing the data. Know how it works. You worked on first time. Trend lines within each category of vegetative type are clearly very different, indicating an interaction between these features. Since knowing BLG type tells us more about how ground living area relates to sale price. We should consider including BLG type in our future set. Trend lines of most sold, however, are almost all the same. Future hasn't become more informative for knowing BLG type. Yeah, I guess I got that when I saw the data. So it's showing that this has stronger correlation. This shows how ground living area has related to price, and the other doesn't so much. First set of development features. Let's take a moment to make a list of features we might focus on. The exercise in lesson 3, you start to build up more informative feature set through combinations of the original features you identified as having high potential. Found You found that the 10 features with the highest MI scores were. Do you recognize the themes here? Location, size, and quality. You need not restrict development to only these top features, but you do now have a good place to start. Combining these top features with other related features, especially those you identify as creating interactions. It's a good strategy for coming up with a highly informative set of features to train your model on. Once you've identified a set of features with some potential, it's time to start developing them. In this lesson, we'll learn a number of common transformations that can do entirely in pandas. If you're feeling rusty, we've got a great course on pandas. We use 4 datasets in this lesson having a range of feature types. The following cell loads them up. Tips on discovering new features. Understand the features, refer to your datasets, data documentation, if available. Search the problem domain to acquire domain knowledge. If your problem is predicting a house price, do some research on real estate. Study previous work. Use data visualization. Mathematical transforms. Relationships among numerical features are often expressed through mathematical formulas, which you'll frequently come across as part of your domain research. Pandas, you can apply arithmetic operations to columns just as if they were ordinary numbers. In the automobile dataset, or in the automobile dataset, are features describing cars engines. Research yields a variety of formulas for creating potentially useful new features. The stroke ratio, for instance, is a measure of how efficient an engine is versus how performant. The more complicated a combination is, the more difficult it will be for a model to learn. Like this formula for an engine's displacement, a measure of its power. Data visualization can suggest transformations, often a reshaping of a feature through powers of or logarithms. The distribution of wind speed in USS accidents is highly skewed. For instance, in this case, the logarithm is effective at normalizing it. In speed or apply and plog fix big access. Check out our lesson on normalization in data cleaning, where you also learn about the box transformation, a very general kind of normalizer. Counts. Features describing the presence of or absence of something often come in sets. The set of risk factors for a disease, say, you can aggregate such features by creating a count. These features will be binary, 1 for present, 0 for absent, or Boolean true or false. In Python, Booleans can be added up just as if they were integers. In traffic, accidents are several features indicating whether some roadway object is near the accident. This will create a count of the total number of roadway features nearby using the sum method. So it makes a data frame that is a boolean of the sum of these things. Could also use a data frame built-in methods to create boolean values. The concrete data set are the amounts of components in a concrete formulation. Any formulation is like one or more components. That is, the component has a value of 0. This will count how many components are in a formulation with the data frames built in greater than GT method. Components, concrete components, GT0. So here is showing greater than 0. Building up and breaking down features. Often you will have complex strings that can usefully be broken into simpler pieces. Some common examples: the numbers, phone numbers, street addresses, internet addresses, product codes, dates, and time. Features like this will often have some kind of structure that you can make use of. US phone numbers, for instance, have an area code that tells you the location of the caller. As always, some research can pay off here. The string accessor lets you apply string methods like split directly to columns. The customer lifetime value dataset contains features describing customer of an insurance company. From the policy feature, we could separate the type from the level of coverage. Create 2 new features from the policy feature through the string accessor by splitting. So it takes the columns and splits them and makes you a string, then splits by space and makes the type and level column. Could also join simple features into a composed feature if you had reason to believe there was some interaction in the combination. So here is doing the opposite. Also our own Kaggle learn. Okay, not gonna read that. Group transforms. Finally, we have group transforms, which aggregate information across multiple rows grouped by some category. With a group transform, you can create features like the average income of a person's state of residence, or the proportion of movies released on a weekday by genre. If you had discovered the category interaction, a group transform over that category could be something good to investigate. So I think I've seen this in previous courses. So it's making the index equal to state and comparing to income, then getting the mean. Income, average income. Yeah, and it's making it equal to this column here. The main function is a built-in data frame method, which means we can pass it as a string to transform. Other handy methods include max, min, median, var, standard, and count. Here's how we could calculate the frequency with which each state occurs in the dataset. So same thing as before, but using count instead. Could use a transform like this to create a frequency encoding for a categorical feature. If you're using training and validation speeds to preserve their independence, it's best to create a grouped feature using only the training set and then join it to the validation set. Use the validation sets merge method after creating a unique set of values with drop duplicates on the training set. So creates the average claim, merge the values into the validation set, drops duplicates. So first drops the ones that has in common, and then it merges. I'm not sure if I got it, everything completely, but so first loading up the libraries. I'm just gonna use XGB regressor in this one. Separating the categories with mean square log error. Creates the cross validation score. And then prepares the data. Let's start with a few mathematical combinations. We'll focus on features describing errors. Create mathematical transforms. Create the following features. Leave lot ratio, the ratio of ground leaf area to lot area. So name of the data frame is X. It when it does this. The ratio of grid leaf area to lot area. Spaciousness, the sum of first and second divided by 2. Not entirely sure how to do this, but it's gonna be something like this. Dot sum divided by the sum of all these things. So 1, 2, 3, 4, 5. So apparently there's something wrong here. Not exactly sure what. Here. So maybe I need to use the plus sign. Oh, here. Forgot the sun. I forgot how to do this. Oh, I should use transform maybe. Yeah, I should use transform. No, but here it is using sun. Maybe I need to put x is equals 1. Can do dot apply and then some. No, but then yeah, it's gonna apply the sum to the columns instead. No, it's not gonna sum the columns, it's gonna apply the sum function to each column. I think I'm just gonna look at the hint. So I need to use the plus sign. If you've discovered an interaction effect between an American future and colorful future, you might want to model it explicitly using a one-hot encoding like so. But that's the next thing. So plus the fuck? It's gonna be a plus. Why is it doing this? Don't understand. Oh my god. So annoying. has to be a better way to do this. Oh, I forgot the X. Ah, fuck. I'm just gonna copy the solution. It's gonna be that anyway. Oh, it's DF, not X. But isn't X the same as DF? Oh, here I forgot the parentheses as well. We've discovered an interaction effect between a numeric feature and a categorical feature. You might want to model it explicitly using a one-hot encoding. So interaction with a categorical. We discovered an interaction between these two things in exercise 2. Now create their interaction features. I'm definitely not gonna remember any of this. At least at first. So I assume categorical gets the categoricals. I'm not sure. So categorical is the BOGD. DG, BODG. Type. Count feature. Let's try creating a feature that describes how many kinds of outdoor areas a dwelling has. Create a feature porch types that counts how many of the following are greater than 0. So that's the transform thing. Or the GD. So data frame and the components greater than sum. Count how many times. How many of the following. Not sure if I have to use count or not. Maybe it's dot transform instead of sum. And then parentheses here. I don't know. Data frame. So it is sum. Let's see if this works. So the sum is outside of the data frame. Oh, maybe it's the X3 here? Yeah. How about that? Yeah. No, I think it's correct. This object has no attribute greater than. So it's count, transform count. This object has no attribute transform. So maybe just count. Dot apply count maybe. So it's saying that. Oh, it's outside here. So maybe it is the other ones that I was trying. Transformer GT. Yeah, because it has to be greater than 0. No, I think it's correct. Oh, okay. So it's the F instead of the X3. Oh yeah, because X3 is a new data frame. They break down a categorical feature. You see that there is a more general categorization described roughly by the first word of each category. Create a feature containing only this first words by splitting a subclass at the first underscore. In the split method, use an argument n equals 1. So it didn't say the type of feature. What name it wants me to give. I'm gonna have to look at the thing. Only these first words. Create a feature containing only these first words. So I guess it's like this. MS class. Did they say that? It was incorrect. I don't understand why. So this is gonna give me a list. So I have to use join, I think. And I need to join with the first two words. Maybe this n equals one already split, already gets the only first. The first two only. Oh, it's a series object. It would be good if I could see what it actually is. Expand equals true. And then there's another thing that I do here. I don't understand. I don't know. I'm gonna look at the solution. Zero. I don't understand why, to be honest. I get that this is splitting, and then it's gonna become a list of these words here. I don't know what the n equals 1 does. Maybe it starts splitting from the first, from the second underscore, and this gets the first item. Maybe that's it. Use a group transform. The value of a home often depends on how it compares to typical homes in its neighborhood. Create a feature that describes the median grouped on neighborhood. That describes the median of ground living area. Oops. So DF group by dots. Median or mean? I don't know. Probably wrong, but so DF group by. I think the first part is correct. Transform. Oh, here. No, it's correct. Maybe if I change to the other notation, it works. Shouldn't make any difference, but incorrect again. Oh, maybe it's just the parentheses here. Not. So it should be this. Median instead of me. Yeah, nice. So far, the course has been very different than what I thought it would be. I thought it would be about hyperparameter optimization. But I think it's also really important, this future engineering stuff. I didn't understand what people mean when they say future engineering, but it's just a fancy way to say manipulating the data points. Introduction. This lesson, the next, make use of what are known as unsupervised learning algorithms. Unsupervised algorithms don't make use of a target. Instead, their purpose is to learn some property of the data, to represent the structure of the futures in a certain way. In the context of future engineering for prediction, you could think of an unsupervised algorithm as a future discovery technique. Clustering simply means the assigning of data points to groups based upon how similar the points are to each other. A clustering algorithm makes birds of a feather flocks together, so to speak. When used for future engineering, you could attempt to discover groups of customers representing a market segment. For instance, or geographic areas that share similar weather patterns. Adding a feature of cluster labels can help machine learning models untangle complicated relationships of space or proximity. Cluster labels as a feature. Applied to a single real valued feature, clustering acts like a traditional binning, binding, or discretization transform. On multiple features is like multidimensional binding, sometimes called vector quantization. Left clustering a single feature, right clustering across two features. Added to a data frame, a feature of cluster labels might look like this. It's important to remember that this cluster feature is categorical. Here, it's shown with a label encoding, that is, as a sequence of integers. As a typical clustering algorithm would produce, depending on your model, a one-hot encoding may be more appropriate. The motivating idea for adding cluster labels is that the clusters will break up complicated relationships across features into simpler chunks. Our model can then just learn the simpler chunks one by one instead having to learn the complicated whole all at once. It's a divide and conquer strategy. Sale price. Clustering the year built future helps this linear model learn its relationship to sale price. The figure shows how clustering can improve a simple linear model. The curved relationship between the year built and sale price is too complicated for this kind of model. It underfits. On smaller chunks, however, the relationship is almost linear, that the models can learn easily. K-means clustering. There are a great many clustering algorithms. They differ primarily in how they measure similarity or proximity and in what kinds of features they work with. The algorithm we use, k-means, is intuitive and easy to apply in a feature engineering context. Depending on your application, another algorithm might be more appropriate. K-means clustering measures similarity using ordinary straight lines distance. Euclidean distance, in other words, so it finds the center of mass, pretty much. You could imagine each centroid capturing points through a sequence of radiating circles, and sets of circles from competing centroids overlap to form a line. The results what's called Voronoi translation. The translation shows you to what clusters future data will be assigned. Let's review how the k-means algorithm learns the clusters and what that means for a future engineer. Focus on three parameters from scikit-learn's implementation: n clusters, max, iter, and n init. The simple two-step process. The algorithm starts by randomly initializing some predefined number and clusters of centroids, then iterates over these two operations. Assign points to the nearest cluster centroid, move each centroid to minimize the distance to its points. It iterates over these two steps until the centroids aren't moving anymore, or until some maximum number of iterations has passed. It often happens that the initial random position of the centroids ends in a poor clustering. For this reason, the algorithm repeats the number of times n in it and returns the clustering that has the least total distance between each point and its centroid, the optimal clustering. The animation below shows the algorithm in action. It illustrates the dependence of the result, the initial centroids, and the importance of iterating until convergence. We may need to increase the max iter for a large number of clusters, or n init for a complex dataset. Ordinarily, though, the only parameter you need to choose yourself is n clusters, k that is. The best partitioning for a set of features depending on the model you're using and what you're trying to predict. This best to tune it like any hyperparameter through cross validations. California housing. As a spatial features, latitude and longitude make natural candidates for k-means clustering. In this example, we cluster this with median income to create economic segments in different regions of California. Since k-means clustering is sensitive to scale, it can be a good idea to normalize extreme values. Our features are already roughly on the same scale, so we leave them as this. Now let's look at a couple plots to see how effective this was. First, a scatter plot that shows geographic distribution of clusters. Seems like the algorithms has created separate segments for higher income areas. The target in this dataset is median house values. This box plot shows the distribution of the target within each cluster. If the clustering is informative, this distribution should, for the most part, separate across median house value, which is indeed what we see. This is pretty much a method to find the center of mass, depending on how many clusters you specify. I think I'm gonna try to finish this one in one go. It's going pretty fast. The k-means algorithm is sensitive to scale. This means we need to be thoughtful about how and whether we rescale our features, since we might get very different results depending on our choice. As a rule of thumb, if the features are already directly comparable, like a test result at different times, then you would not want to rescale. On the other hand, features that aren't on comparable scales, like height and weight, will usually benefit from rescaling. Sometimes the choice won't be clear though. In that case, you should try to use common sense. Remember, the features with larger values will be weighted heavily. Scaling features. Consider the following sets of features for each. Decide whether they definitely should be rescaled. They shouldn't be. Either might be reasonable. Latitude and longitude, lot area and living area of houses, number of doors and horsepower. So I think the third one should be the second one. Lot area. Probably the first two not. The third yes. I'm not sure. No, since rescaling would start, either choice would be reasonable. Yes. Oh, okay. Makes sense. Create a feature of cluster labels. Creating key means clustering with the following parameters. Features, number of clusters, iterations done. They take a moment to complete. This may take a moment to complete. Find a list of the features to be used for clustering. So X, Hopefully this time doing like this will work. Just getting the columns that I wanna apply the thing to. Okay, means I think I forgot how to specify it, but n clusters was done. S type category. No, K means fit predict. K means, which is this object that I created. Fit predict. Underscore predict the futures. So here's a rescaling. It's getting all the rows for the futures columns. X scaled minus X mean, X is 0. This gets the mean of every row and subtracts from the, so it's subtracting the mean from the columns to make all the values on a similar scale. Is dividing by standard deviation, which is a normalizing method. Hopefully this will work. Again, same problem. Maybe it's but it's supposed to be a df copy. I don't understand why this is not getting the columns. It should be. Oh, maybe it's just fear. But then it's the same thing. My mind. Just do it like this. So maybe I should do it like this. But this is not gonna work for sure. Yeah. I don't understand what's going on. So it doesn't have the X. And it needs. Which I forgot. So any needs is how many times it's gonna run. Until it finds the center. It repeats a number of times. I'm gonna put the same number of columns, which is 5. So maybe this works. Do not convert string to float, lot area. Yeah, if it's a categorical, it should hot encoding. Apply one hot encoding or the other encoding before, but exercise is not telling me to do that. maybe if I put X futures here again. I don't know. I'm gonna look at the solution. Well, futures doesn't work. X futures doesn't work as well. Maybe just price. Maybe it's Y here. But that doesn't make sense. Beat the K-means model check scaled and create. Oh, so maybe. Well, maybe it's X scaled here. And create the cluster labels. Yeah, because it's taking the futures here and then it's using here to define X scaled. So maybe the first one is fit predict. But then it should have one more line here, not just true. As type category. Yeah, I think I'm gonna look at this solution here. But first I'm gonna go to the ref bread back. So I have no idea why this is wrong. Next scale. Yeah. So what's wrong with my thing? Clusters stand. Oh, and it needs to stand. Maybe that's what's the problem. Yeah. But I don't know how I'm supposed to know that is equals 10 and not 5 or not some other number. Yeah, I don't know. The K-means algorithm offers an alternative way of creating features. Instead of labeling each feature with the nearest cluster centroid, you can measure the distance from a point to a centroid. Cluster distance feature. Now add the cluster distance feature to our dataset. Get these distance features by using the fit transform method of K-means instead of fit predict. Create the cluster distance feature using fit transform. K-means dot fit transform. I guess it's gonna be the same parameters. So maybe there doesn't have any parameters on the current position environment. Next scale. So I think it's either X scale, X clustered, or yeah. That should be X scale. So, but why did it say that's not defined? Maybe I typed the wrong way. Yeah, it doesn't make any sense. It's exactly what I did. Fit transform. What the fuck? Maybe there's something that I'm missing here. It's exactly the same in my mind. I can't see anything. Maybe it's a typo somewhere. Looks like it's the same thing. Maybe it's a problem with the thing itself, the notebook. It's copy exactly the same. And it's still giving the error. And I'm using the solution. So yeah, I don't know what's wrong with this. Columns overlap and no suffix specified. I guess this is this part that's wrong, probably. Yeah, I have no idea. The previous lesson, we looked at our first model-based method for feature engineering, clustering. This lesson, we look at our next principal component analysis, PCA. Just like clustering is a partition of the dataset based on proximity, you could think of PCA as a partition of the variation in the data. PCA is a great tool to help you discover important relationships in the data. It can also be used to create more informative features. Technical note: PCA is typically applied to standardized data. Standardized data variation means correlation. When standardized data variation means covariance. All data in this course will be standardized before applying PCA. In the abalone dataset are physical measurements taken from several thousands of Tasmanian abalone. I'm not gonna read all this stuff. Often we can give the names of the axis variation, the longer axis. Yes, just explain the data. The new features PCA constructs are actually just linear combinations, weighted sums of the original features. The new features are called the principal components of the data. The weights themselves are called loadings. There will be as many principal components as there are features in the original dataset. If we had used 10 features instead of 2, we would have ended up with 10 components. Components loading tell us what variation it expresses through signs and magnitudes. This table of loadings is telling us that in the size component, height and diameter vary in the same direction, same sign. When the shape component, they vary in opposite direction. In each component, the loadings are all of the same magnitude, and so the features contribute equally in both. PCA also tells us the amount of variation in each component. You can see from the figures that there is more variation in the data along the size component than along the shape component. PCA makes this precise through each component's percent of explained variance. Size accounts for about 96% of the shape, for about 4% the variance between height and diameter. The size component captures the majority of the variation between height and diameter. It's important to remember, however, that the amount of variance in a component doesn't necessarily correspond to how good it is as a predictor. It depends on what you're trying to predict. PCA for feature engineering. There are two ways you could use PCA for feature engineering. The first way is to use it as the descriptive technique Since the components tell you about the variation, you could compute the MI scores for the components and see what kind of variation is more predictive of your target. That could give you the ideas of what kinds of features to create a product of height and diameter if size is important, say. Variation of height and diameter shape is important. You could even try clustering on one or more high scoring components. Second way is to use the components themselves as features. Because the components expose the variational structure of the data directly, they can often be more informative than their original features. Here are some use cases: dimensionality reduction, anomaly reduction, noise reduction, the correlation. PCA basically gives you direct access to the correlational structure of your data. No doubt come up with applications of their own. Example, automobiles, safe, transform. Defining the PCA instance contains loadings in its components attribute. Recall that the signs and magnitudes of a component's loading tell us what kind of variation it's captured. First component shows a contrast between large, powerful vehicles and with poor gas mileage and smaller, with more economical vehicles with good gas mileage. Mileage. We might call this the luxury economy axis. As figure chosen. Let's also look at the MI scores of components. Not surprisingly, PC1 is highly informative. Though there are many components, despite their small variance, we still have a significant relationship price. Examining those components could be worthwhile to find relationships not captured by the main luxury economy. Third component shows a contrast between horsepower and curb weight. To express this contrast, let's create a new relation. Not sure if I got everything, but I don't know. I think this is gonna be better to learn from a video instead of the course. Create principal components. Be safe, it transform component names. Plot variance. MI scores. Let's choose a few features that are highly correlated with our target sale price. We rely on PCA to untangle the correlational structure of these features and suggest relationships that might be usefully modeled with new features. Run the cell to apply PCA and extract the loadings. Interpret component loadings. Look at the loadings for components PC1 and PC3. Can you think of a description of what kind of contrast each component has captured? PC1 and PC3. So there's negative correlation for PC3 and positive for PC1 on the first three things. I don't really understand this though. What's the difference between each of them? After we thought about it, run the next cell for a solution. The first component, PC1, seems to be a kind of size component similar to what we saw in the tutorial. All of the features have the same sign, positive, indicating that this component is describing a contrast between houses having large values and houses having small values for these features. The interpretation of the third component is a little trickier. The features garage area and year remote add both have near zero loadings. That is true. So let's ignore those. This component is mostly about total. It describes a contrast between houses with a lot of living area but small, no existing basements, and the opposite, small houses with large basements. Your goal in this question is to use the results of PCA to discover one or more new features that improve the performance of your model. One option is to create features inspired by the loadings, like we did in the tutorial. Another option is to use the components themselves as features, that is, add one or more columns of XPCA tracks. Add one or more new features to the dataset X. For a correct solution, get a validation score below 0.14. If you get stuck, feel free to use the hint below. Yeah, so I have no idea. No idea. Describes a contrast between houses with a lot of living area but small or no existing basement. And the opposite, small houses with large basements. So maybe a ratio between the two. BSMT round ratio. Going for the easy one first. I don't know if this was your score 0.14, you need to score less than 0.14. Okay, so at least I got I score. Let me try the other way around, see if it makes any difference. Probably not. So this doesn't work. So I'm gonna put the third XPCator PC3. I'm not sure to put the PCA though. Oh, it's the correct way to put this. This probably doesn't work. PC3. PC3 is not defined. So how can I put this column there? Maybe it's just to put on a string instead here. Yeah. So not sure. Don't know. Maybe one divided by the other. This doesn't work. I'm just gonna look at the hint or the solution. Probably the hint first. At least this is closer than the other ones I got. Try using the make me scores function on XPCA to find out which components might have the most potential. Make me scores. So it's this function. Then look at the loadings to see what kinds of relationship among the features might be important. So I think he wants me to do this, but it doesn't make sense. I don't really understand that well. What this does? What is PCA and uh, how is it making this equal to this? Alternatively, you can use the components themselves. Try joining the highest scoring components from XPCA tracks. Just join all of XPCA tracks. Best far. So we have to specify axis here. X1. Or I can do one plus the other manually. I'm gonna look at some videos after I'm finished with this course about PCA. It when it gets. Oh, there we go. It's probably not gonna work. Okay, so closer, but didn't work. What if I PCA C1 2 3? So it still doesn't work. I'm gonna look at the solution then. X equals the F copy. X join XPA. So it's just joining the other. Yeah, makes sense. What's the solution one? So first makes one plus the other, multiplies this two. Yeah. Next question explores a way you can use PCH to detect outliers in data sets. Blah blah blah. So it's creating a graph with the PCAs. As you can see, in each of components, there are several points lying at the extreme ends of the distribution. Now run the next cell. Just see the houses that sit at the extreme of components. So the first ones are the outliers, I guess. Do you notice any patterns in the extreme values? Does it seem like the outliers are coming from some special subset of the data? Yeah. After you thought about your answer, run the next cell for the solution. Notice that there are several dwellings listed as partial sales in the AdWords neighborhood that stand out. A partial sale is what occurs when there are multiple owners of a property and one of or more of them sell their partial ownership of the property. These kinds of sales are often happen during the settlement of a family estate, the dissolution of a business, and aren't advertised publicly. If you're trying to predict the value of a house on the open market, you would probably be just fine removing these sales like this. On the other side, they're truly outliers. Save. So I think the last tutorial is the last one. The next tutorial is the last one, I should say. It's almost 2 hours now. Tutorial. Target encoding is any kind of encoding that replaces the features categories with some number derived from the target. Simple and effective version is to apply group creation from lesson 3, like the mean. Using the automobiles dataset, this computes the average price of each vehicle's make. So grouping by price, per make, and comparing price to price, and getting the mean. And creates this table here. This kind of target encoding, this series, I should say. This kind of target encoding is sometimes called the mean coding, applied to a binary target. It's also called bean counting. Other names you might come across include likelihood encoding, impact encoding, leave one out encoding. Smoothing. An encoding like this presents a couple of problems, however. First are unknown categories. Target encodings create a special risk of overfitting, which means they need to be trained and on an independent encoding split. Enjoy the encoding features. These missing values was second are rare categories. Categories only occur a few times. Solution to this problem is to add smoothing. The idea is to blend the in categories average with the overall average. Rare categories get less weight on their category average, while missing categories just get the overall average. Pseudocodes, coding, weight times in category plus 1 minus the weight dot overall. Where weight is a value between 0 and 1 calculated from the category frequency. Use weight to determine the value for weight to compute an M estimate, where n is the total number of times the category occurs in the data. Parameter m determines the smoothing factor. Larger values of m put more weight on the overall estimate. Category weight, category count. The automobiles dataset, there are 3 cars with the make Chevrolet. If we chose M2, then the Chevrolet category would be encoded with 6% of the average Chevrolet price, plus 5% of the overall average price. When choosing a value for M, consider how noisy you expect the categories to be. Does the price of a vehicle vary a great deal within each make? Would you need a lot of data to get good estimates? If so, it could be better to choose a larger value for M. If the average price for each make were relatively stable, smaller value could be okay. I think I'm just gonna skip through this. First, you need to choose which features you want to apply a target encoding to. Categorical features with a larger number of categories are often good candidates. So run this cell. Talked about how the M estimate coding uses is moving to improve the F. Not fine. It didn't run this first cell. Talked about how M estimates encoding uses moving to improve the estimates for higher categories. To see how many times a category occurs in the dataset, you can use the value counts method. This cell shows the counts for cell type, but you might want to consider others as well. Okay, now it works. Value count. Which features did you identify for target encoding? After you've thought about your answer, run the next cell for some discussion. I think the first ones happen more often. Neighborhood future looks promising. Uh, yeah. It has the most categories of any future. Several categories are rare. So I guess it's on this list here. If it was sorted, it would be easier. But here, neighborhood 28. So it's pretty much based on how many different categories the column has. The more, the better. Others that could be considered is, in fact, almost any of the nominal features would be worth trying because of the prevalence of rare categories. Now you apply targeting encoding to your choice of feature. As we discussed in the tutorial, to avoid overfitting, we need to fit the encoder on data held out from the training set. Run this out to create the encoding and training splits. Apply estimate encoding. Apply target encoding to your choice of categorical features. Also choose a value for this moving parameter m. Any value is okay for a correct answer. So I'm not sure if I should make this on the same line or if I'm supposed to do everything on the same line or use your line. Or maybe I can use any m that I want. Yeah, so it's gonna be this thing here. And the calls are gonna be the ones that they say here. Fit encoder on the coding split. Coder dot fit predict or transform. That's fit. X retrain y train. See if this works. Incorrect value for X train. So maybe this is X in code. No, but doesn't make much sense. No, actually does. Because I'm coding first and training after encoding. If you'd like to see how the encoded feature compares to the target, you can run this cell. So this is the graph. Run the distribution plots. Does it seem like the encoding is informative? In this cell, we'll show you the score of the encoded set compared to the original set. Do you think that so baseline score of encoder, so it's actually worse than the other one? Do you think that that target encoding was worthwhile in this case, depending on which feature or features you chose? May have ended up with a score significantly worse than the baseline that case, it's likely that the extra information gained by the encoding couldn't make up for the loss of data used for the encoding. This question will explore the problem of overfitting. So let's see what happens when we fit the encoder and the model on the same data set. To emphasize how dramatic the overfitting can be, we mean encode a feature that should have no relationship with sale price. Account. So xcount range length x. Actually need one duplicate value to circumvent error checking. MS mirror. It is not a swarm, the same data set. Just taking the columns and close them. Almost a perfect score. Overfitting with target encoders. Based on your understanding of how mean encoding works, can you explain how XGBoost was able to get an almost perfect fit after mean encoding the count feature? No, honestly. Since count never has any duplicate values, the mean coded count is essentially an exact copy of the target. In other words, mean coding turns a completely meaningless feature into a predicted perfect feature. Now, the only reason this worked is because we trained XGBoost on the same set we used to train the encoder. If we had used a holdout set instead, none of this fake encoding would have transferred to the training data. The answer is that when using a target encoder, it's very important to use separate data sets for training the encoder and training the model. Otherwise, the results can be very disappointing. That's it. So I didn't really enjoy this course that much, to be honest. I think the other ones were better. But maybe it's because I don't see how immediately how useful this can be in practice. I think the videos will teach me more about it. Okay. Yeah, I knew this would be incomplete because of that question that wasn't working. I'll probably do the next course, the line after this one. Intro to SQL. SQL. Yeah, I think I'll do this in order. It is here now, from now on. Seems like a good progression. Except for this Python one that I think is too basic. It's 1, 2, 3, 4, 5, 6, 7. There's still 10 more courses to go. So I'm not sure if it worked. No, now it's showing correct. So it was probably a problem. Maybe I didn't run the previous cells correctly. That's why it wasn't working there. So yeah, I'm done for now, and might come back later on to watch some videos and to work on other stuff. But if not, I'll probably come back another time and continue these courses on Kaggle. So see ya.